Hello and welcome to Statistics Day 3. A couple questions on the homework I think we should go over first. The first one is number 4, which always gives a lot of people trouble because it's kind of an annoying one. It says the weights of 4-year-old boys are normally distributed with a mean of 38 pounds and a standard deviation of 4 pounds. Which the following weights could represent the 90th percentile of the weight of a 4-year-old. So I really recommend when you start seeing the word percentile, oops, to circle it and write at or below, because that means you're looking for which one has a percent at or below that gives you 90. So if you think of the situation we're in here, we have normal curve. Mean is 38 pounds, so that's going to go over here. The 90th percentile, you need 90% of the data to be at or below. So 90th percentile would be over here somewhere. You have to look something like that. Now the problem is all of these could go somewhere over there. There's nothing that's below 38. They're all possible to be the 90th percentile. Now I would say maybe 41 is a little bit low. I don't know if 41, since the standard deviation is 4 pounds, that's not even one standard deviation above the mean. So that's kind of high, kind of low to have 90% of the data below it. So I would maybe think probably not that one. 45 pounds, you could maybe see that one. 47 by the same token might be kind of high. That's a lot above. So I'd say more than 90% of the data would be below that. So I'm kind of narrowing it down to these two. So let's try 45. First, you need to find a z-score. So the z-score for 45 would be the observed 45 minus the mean 38 divided by the standard deviation, which is 4. And 45 minus 38 divided by 4, let's see, 45 minus 38, hit enter, divided by 4, that's 1.75. So if I wanted to see what percentile that was, I would do normal CDF. My low, I'm going down forever because everything at or below. So that's negative infinity, negative 1 times 10 to the 99th. My high would be 1.75 with a mean of 0 and a standard deviation of 1. And let's see what that gives us. So second distribution, normal CDF. We've got negative infinity already in there. Put 1.75 right here. Mean of 0, standard deviation of 1. That's what we always have. And that's 0.96. So that's really at the 96th percentile. That's too big. So if that's too big, we know 47's out. It's 43 or 41. Now again, I said 41 seemed low to me, so let's try 43. So find your z-score, 43 minus 38, all divided by 4. So 43 minus 38, hit enter before you divide by 4, or use alpha y equals, and you get 1.25. So then we have normal CDF, negative infinity again, because we're going at or below. High would be 1.25, 0, 1. So we're going to have almost the exact same thing. The only thing that's changing is my upper value is 1.25 now. $89.4, that's about the 90th percentile. So certainly, really it's the 89th percentile, so it's not perfect. But we'd say about the 90th percentile, and it doesn't say exactly, it just says could represent the 90th percentile. So we'll go with that one because that's as close as we're going to get, because that's going to be too low. Because if this is 89, 41 is obviously going to be lower than 89. Okay, so that's how you do that one. The other one I wanted to go over was the last one. It's another percentile question. At the beginning of April 2016, the national gas average was $2.06 per gallon. At that same time, the New York gas average was $2.11 per gallon. Assuming gas prices in the U.S. are normally distributed with a standard deviation of 26 cents per gallon, at what percentile does the New York State gas average fall at this time? Again, at what percentile? What are you going to write? At or below. Okay, so as soon as you see normally distributed, you want to draw your normal curve. In the middle of it, you want to put the average, which was 2.06. New York gas average was 211, so it's going to be up here somewhere. So your first step is to find the z-score. So observed is 211 minus the average, $2.06, divided by the standard deviation, 26 cents. So you can do 2.11 minus 2.06. Hit enter before you divide by the standard deviation. Z-score is 0.192-ish. It's better not to round this if you can handle it, but I know we have a big number there. Okay, so now we do normal CDF. And if I'm looking for a percentile on my picture, I'm always shading below, because percentile means at or below. So it's going to be that -1 times 10 to the 99th number again for negative infinity. My upper value is going to be that 0.192 number. We standardized it with a z-score, so comma 0, comma 1. Let's see what we get. So the upper is 0.192-ish. Rounding edge to the nearest whole number, so when I hit enter, 0.576. So that's the percent of the data that's below it. Move the decimal place 2 to the right, because we're talking percentile, so you want to get the percent. 57.6 is about equal to the 58th percentile. Okay? So percentile, you really got to know it means at or below. All right, let's switch over to warm up. It says assume that the ages of first-year college students are normally distributed with a mean of 19 years and a standard deviation of 1 year. To the nearest integer, find the percentage of first-year college students who are between the ages of 18 and 20 inclusive. And then for the second part, find the percentage of first-year college students who are 20 years old or older. Hit pause if you had trouble on yesterday's homework at all, and give this a shot. Find the z-scores, use normal CDF, give me my answer to the nearest percent for the integers. Go for it. All right, I'm assuming you've tried it. Here's how you do it. Draw the normal curve. Every time you need a picture. Find the percentage of first-year college students who are between 18 and 20. Okay, so the mean is 19, and the standard deviation is 1. So 19 goes here. Standard deviation of 1 means if I want between 18 and 20, we'd have 18 over here, we'd have 20 over here. Now, I already know, just so you make sure you know what normal curve means, the mean is always at 0. Since standard deviation is 1, this is going to be +1, this is going to be -1. Because if I add 1 to 19, I get 20. If I subtract 1 from 19, I get 18. That's what a z-score does. A z-score tells you how many standard deviations away you are. So if I did 18 minus the mean over the standard deviation, that's -1, just like we said it would be. And if I do my second z-score, 20 minus 19 over 1, that's +1, just like we said it would be. So now if I want it between those two, I'll just do normal CDF. Low is -1, high is 1, mean is 0, standard deviation is 1, because that's what z-scores do. So second vars, normal CDF, lower is -1, upper is 1. That's why you need your picture. Look from the lower shaded to the upper shaded, 0 and 1. And we get 0.682, so to the nearest integer, be 0.68. or 68%, because it asks for the percentage. Okay, then for part B, to the nearest integer, find the percentage of first-year college students who are 20 years old or older. Same idea. Mean is still 19. This time, though, we're looking for 20 years or older, so I would shade it this way. Now, from our work before, we already know that our z-score is over at 1. So I would do normal CDF. This time, my min is 1, or my lower is 1, because that's the lowest shaded. My upper would be infinity, 1 times 10 to the 99, comma 0, comma 1. And I get 0.1586. So if you make that into a percent, it's 15.8. Nearest percent would be about 16%. Sorry, I got the same random fact as yesterday. Okay, so I want to connect one more time, and you'll see this in the notes. What the z-scores in this normal CDF is doing is it's making it so you could use this chart. Now, this chart is if you didn't have a calculator. I'm trying to use it to show you what the calculator's figuring out. For this first one, we were looking at percentage between 18 and 20. That was from -1 standard deviations to +1. So that would be from here to here. And if you add these up, we have 19.1 plus 19.1. Okay, so that's 38.2. 15 and 15 is 30. So 30 plus 38.2 would be 68.2%. So 68.2% of the data fall between -1 and 1. That's what we got right here, 68.2%. Literally the exact same thing. The calculator is doing this work for you. Same idea with the second one. I wanted the percent that was bigger than 1, and I got 16%. So bigger than 1 would be from here over. And if I add up all these percents quick, 9.2 plus 4.4 plus 1.7 plus 0.5 plus 0.1, 15.9, again, literally exactly what we got, 15.9%. So I want you to understand that normal CDF is the same as doing this. And that's what we're going to look at the start of the notes. So today is nothing super new, but I'm going to start by going through that connection again, and then at the end I will show you a shortcut. So how do you know to use the word, or to use the normal curve? Well, it's pretty easy. You look for the phrase normally distributed or something similar. So a lot of things in math can be tricky because you don't know what to do when. Not the case with normal curve. The problem has to say something about it being normally distributed. So here's our first example. The weights of Siamese cats are normally distributed with a mean of 6.4 pounds and a standard deviation of 0.8 pounds. If a breeder of Siamese cats has 128 in his care, how many can he expect to have weights between 5.2 and 7.6 pounds? Okay, there's that word, normally distributed. As soon as I see that, I kind of just immediately draw this picture and don't even finish reading for a second. Okay, now once I finish reading, we always know what goes in the center. The mean, so that's 6.4 pounds. And I want how many have weights between 5.2 and 7.6. Okay, well 5.2 pounds would be down here, 7.6 would be up here, and I want how many are between. Okay, so just like the warm-up, your first step is to find your two z-scores. So the lower one would be 5.2 minus the mean of 6.4 divided by the standard deviation, 0.8. And the upper one would be 7.6 minus 6.4 divided by 0.8. Okay, so I can use my calculator to find both of those. And you can use alpha y equals, or you can just be careful. 5.2 minus 6.4, hit enter before you divide by 0.8. So there's your lower z-score. And my upper one is 6.7 minus 6.4, hit enter, divided by 0.8. So I'm going from negative 1.5 to positive 1.5. Okay, so next I would go to normal CDF. My lower would be my lower z-score of negative 1.5. my upper z-score of 1.5. And as far as you know right now, mean is always 0, standard deviation is always 1. So second bars, normal CDF, going from negative 1.5 to positive 1.5, comma 0, comma 1, 0.86638, blah, blah, blah. Now think of what that means. That means about 86.6% of the data is between these values right here. Or so about 87% of his 128 cats. Because this question specifically said how many. When you see how many, you got to remember that this is a percentage that they're giving you. So if I want an actual number of how many cats, I would take that 128, multiply it by that percentage we got, and it's better not to round it. Since it's on my calculator anyway, I can just do 128 times that answer, and I get about 111 cats. And I would just round it like normal. You can't have a percentage of a cat. Okay? So that takes you through pretty much what we did yesterday. The only difference here, I don't think we had any how many questions yesterday. That just means multiply by the number. Okay, let's do another example. Scores on a standardized test are normally distributed with a mean of 560 and a standard deviation of 75. Answer the questions that follow. Find the probability that a test picked at random would have a score larger than 710, round to the nearest tenth of a percent. Okay. So I see the word normally distributed. That's what's important. That means I'm allowed to use this. We're going to have 560 in the center because the mean's always in the center. Standard deviation of 75, we'll need that. We want the probability that a test picked at random would have a score larger than 710. So larger than 710 would be here. What would I do next? Z-score. So the observed is 710 minus the mean, 560, divided by the standard deviation, which we said was 75. 710 minus 560, hit enter, divided by 75, 2. So it's just 2 standard deviations above. And I want to make sure you understand the 2 differences, or that you're really doing the same thing. You could use graph because 2 is on the graph. So if you look at that graph that we did, where 0's in the middle, 2 is up here, I'd want everything over here. So let's look at that graph real quick. I'd be looking, here's 2. I'd be looking for everything over here. So 1.7, 0.5, 0.1. 1.7 plus 0.5 plus 0.1. What's that going to be? That's just 1.7 plus 0.6 if I add those two together. 2.3. So the nearest tenth of a percent, we've got a 2.3% chance that the score falls up there. Or you don't have to use the graph or use calc. On the calculator, you would have normal CDF. Looking at your shading, your lower would be 2. Your upper would be infinity, 1 times 10 to the 99th. And at this point, we've always been using 0, comma 1, because using a z-score normalizes it with 0 and 1. Okay, so I could do second vars, normal CDF, lower is 2, upper is infinity, mean is 0, standard deviation, because we're using z-scores, 0.02275. And that's the probability to the nearest tenth of a percent, 2.27. Look, you get the same thing, 2.3%. So the calculator can give you a little bit more accurate answers. I could go out to the nearest hundredth or whatever I wanted to. But the graph gives us the exact same answer. So I'm trying to show you this so that you get that normal CDF is doing the same thing as adding up the percents under the graph. Okay? Part B, determine the percentile of a test score of 447.5. What's percentile mean? At or below. Hopefully you're screaming that at the video at this point. So my picture would look like this. Again, we've got our mean of 560 on the percentile of someone who gets a 447.5. At or below means you shade at or below. You find your z-score. So 447.5 minus 560 divided by 75. 447.5 minus 560. Hit enter, divided by 75, negative 1.5. Okay, so again, you could use the graph because negative 1.5 is on the graph. We've got 0 here, negative 1.5 here, and I want this percentage. So if I wanted to use the graph, I'd look at negative 1.5, which is right here, and I'd add up all the percentages at or below. So 0.1, 0.5, 1.7, 4.4. 0.1, 0.5, 1.7, 4.4. So I know the first three give me 2.3. We did that. So add 4.4 onto that, and we get 6.7. So that is the 6.7th percentile. Okay? Or you could use calc. And the calculator would just be normal CDF, negative infinity, so negative 1 times 10 to the 99th, up to negative 1.5, comma 0, comma 1. And let's see what we get. Normal CDF, we got negative infinity, negative 1 times 10 to the 99th. Upper is negative 1.5, comma 0, comma 1. 0.0668. And we're talking percentile. Look at that, 6.7th percentile. You get the same thing. Okay, so I hope that clears up what the calculator is doing. Now with those, I could use the graph or the calculator because my z-score came out to be a number that was on the graph. If you turn to the next page, last part of this question, find the probability to the nearest hundredth that a completed test picked at random would have a score between 500 and 600. Would start the same way. So the mean was 560. So this is still the same setup. So I want between 500 and 600. Means I want from here to here. There's my lower and upper. So I've got two z-scores to find. My lower one, 500 minus 560 divided by 2, and my upper one. So 600 minus 560 divided by 2. $500 minus 560, enter, divided by 2. Sorry, what am I doing 2? What was the standard deviation? 75. Sorry about that. Went crazy for a second. But I'm back. Okay. So negative 60 divided by 75. This top one is going to end up being negative 0.8. And my lower z-score, 600 minus 560, that's 40, divided by 75 is 0.53 repeat. Now in this case, I don't have an option. I can't use this because negative 0.8 and 0.53 repeat aren't exactly on the graph. I could estimate it, but I don't know how to add these up. I wouldn't get a very good estimate. So the calculator always works. These are not nice z-scores. And that just means they're not on the graph. So the only way to answer this is with the calculator. Must use calc. So normal CDF. What's your lower? The lower z-score, negative 0.8. Your upper would be 0.533 repeat. We've always been doing comma 0, comma 1. And I can do second bars, normal CDF, negative 0.8, 0.5 with a bunch of 3s, comma 0, comma 1, 0.4912. So to the nearest hundredth, the probability would be 0.49. So about a 50% chance. All right, so the purpose of all of that was to show you what the calculator is actually calculating, but I don't ever use the graph. I just always go straight to the calculator because you can use that for every problem. The graph only works when these come out nice. So just use normal CDF always, and you should get the right answer. Now, why have we always been using the mean of 0 and a standard deviation of 1? Well, that's because z-scores relate our given situation to, I'm going to call it the parent normal curve. That graph is the parent normal curve. With mean equals 0 and standard deviation of 1. So if I'm using z-scores, it's relating to the mean being 0 and the standard deviation of being 1. But if the calculator is letting us enter in mean and standard deviation anyways, why do we even do that step? Well, from a teaching standpoint, the only way reason I did that whole step was to show you how the calculator's normal CDF is related to the graph. I wanted you to understand what normal CDF was calculating. And now that I think you've got that, we can actually take that step out. So when I do normal CDF, we can just put our lower value, not a z-score, and we can just put our upper value, not a z-score, and we can put the actual mean and the actual standard deviation. Look at this last one we just did. Hang on one second here. So look at this last example we just did. If I had just done second distribution normal CDF and said my lower was 500, because I was between 500 and 600, with a mean of 560, because that was in the middle, and a standard deviation of 75. And if I had done that and bypassed the whole z-score thing, we get the exact same number. So you don't even really need to do the z-score step. You can just draw your picture and type that straight in, and you're done. And that's what I'm going to tell you to do from here on out. On tonight's homework, you really don't need to be doing any z-scores. So that's the shortcut. Let's do that rest of these this way. The lengths of full-grown sockeye salmon are normally distributed with a mean of 29.2 inches and a standard deviation of 2.4. Find the z-scores for sockeye salmon whose lengths are 25 to 32 inches down to the nearest hundredth. Okay, so I just told you didn't have to do this anymore, but just to take you through this, lower is 25 minus the mean of 29.2 divided by a standard deviation of 2.4. And I have to find the other one too. So 32 minus 29.2 over 2.4. So this is our old way of doing it right now. 25 minus 29.2, hit enter, divided by 2.4. That's negative 1.75. And my upper, 32 minus 29.2, hit enter, divided by 2.4, 1.16, repeating. Oh, but I did say nearest hundredth, so 1.17. Using the z-scores you calculated, determine the proportion of sockeye salmon to the nearest percent that lie between 25 and 30 inches. Okay, so here's my picture. We've got 29.2 in the center. We're going from 25 to 32 inches. So using the z-scores, my old way of doing it would have been to say normal CDF. My lower would be negative 1.75, my upper would be 1.17, comma 0, comma 1, because we're going to that parent normal curve again. So negative 1.75 to positive 1.17, comma 0, comma 1, 0.8389. So to the nearest percent, we'd have an 84% chance. Now it says, now instead of using z-scores to determine the proportion, specify the mean and standard deviation in your calculator. So this is our new way of doing it. Now instead of all that z-score step, I could just do normal CDF and look right at your picture. Your lower is 25, your upper is 32, with a mean of 29.2 and a standard deviation, we said 2.4. So the calculator is kind of doing the z-scores for you as part of their calculations. 25, 32, a mean of 29.2, and a standard deviation of 2.4. Look at that, almost the exact same thing. They're only off slightly because we rounded our upper z-score. So the second answer, 0.83826, is actually more accurate. It's not using that rounded z-score. Regardless to the nearest percent, it's still 84%. Okay, so again, only do this new way from here on out. Don't do z-scores. That was just to help you understand what's happening. Now we're doing it the easy way. All right, last page. Let's try to go quick through these. Given that the volume of a can of pop in a 12-ounce bottle from a factory varies normally with a mean of 12.2 ounces and a standard deviation of 0.6 ounces, determine the probability that a bottle chosen at random would have all these volumes rounded to the nearest 10,000. So that's 4 decimal places. So on your homework in here, I still want pictures. I want to see that. So still draw pictures. Okay, so greater than 13 ounces. Okay, well, the mean is 12.2. That's going to go in the center of all my pictures. So 13's over here, and I want greater than 13. So I want the picture, and then I want your normal CDF. So my lower is 13, my upper is infinity, with a mean of 12.2 and a standard deviation of 0.6. And we can type that in right away. So second bars, normal CDF, going from 13 to infinity, with a mean of 12.2 and a standard deviation of 0.6. And the nearest 10,000, so 4 decimal places, would be 0.0912. So a pretty low chance that it'd be that heavy. But look at how much faster that is than doing all the z-score stuff. Okay, so for the middle one, less than 11 ounces. Okay, your mean is still the same. Now 11's down here, and I want less than 11. So I'm just going to type in normal CDF. My lower, I'm going all the way left forever, so negative infinity to 11, with a mean of 12.2 and a standard deviation of 0.6. Again, no z-scores necessary. Normal CDF, my lower is -1 times 10 to the 99th. I'm going up to 11. Mean and standard deviation are the same. 0.0228 if I'm rounding to the nearest 4 decimal places. Again, pretty low percent chance that it's that light. And the last one is between 11.5 and 12.5 ounces. I expect this probability to be a little bit higher because it's where most of the data is. Okay, so we're going to do normal CDF. What's your lower this time? 11.5 up to 12.5 with a mean of 12.2 and a standard deviation of 0.6. Okay, so one more time. Normal CDF, 11.5 to 12.5, mean and standard deviation, 0.5698 if I'm rounding. Okay, so look at how much faster that is. Taking out that z-score stuff should make these go way faster for you. Okay, last example. The average rent for a one-bedroom apartment in the winter of 2015 in New York City was $2,800.01 per month, with a standard deviation of $920. If rents are normally distributed, so now I'm allowed to do my normal curve, what percent of the apartments will be less than $2,500 per month, rounded to the nearest percent? So what goes in the center this time? 2,801. We want less than $2,500. So I would think most rents would be less than $2,500. So all we have to do is normal CDF. What's my lower? Negative infinity. What's my upper? 2,500 with a mean of 2,801 and a standard deviation of 920. So normal CDF, negative infinity, the mean of 2,500. Oh, sorry, upper 2,500, mean is 2,801, and the standard deviation is 920. 0.37176. So to the nearest percent, what would that be? 37%. Okay, part B. If rents are normally distributed, how realistic is it to believe that you will be able to rent a one-bedroom apartment for less than $1,500 per month? All right, well, it would help us to know what's the percent chance that I can find rent that cheap. So here's 2801, mean in the center. 1,500 would be way over here. My gut says not too realistic, but let's check what percent chance we have. So normal CDF, still negative infinity. We want less than 1,500, up to 1,500, with a mean of 2801 and a standard deviation of 920, because that hasn't changed. Okay, so negative infinity to 1,500 is all that's changing. 0.0786. So that's about an 8% chance. So there's only, it says how likely. There's only an 8% chance of finding rent that low. So 8%, I wouldn't say that's likely. It's not impossible. So I would say not likely, but not impossible. Probably not getting a very good apartment. Oh, sorry, not impossible. So not likely, but also not impossible. And finally, a one-bedroom apartment on the Upper East Side with a doorman and views of Central Park is listed at $5,000 per month. How rare is this? So still assuming the rents are normally distributed. So 2801 is in the center. How rare is it to get something that expensive? So if we're talking about that expensive, I'd be thinking more this way. It wouldn't be rare that it'd be 5,000 or less, but how rare is it to have that high of a rent? So 5,000 or more. So let's check normal CDF. This time my lower is 5,000. My upper would be 1 times 10 to the 99th with a mean of 2801 and a standard deviation of 920. So one final time, 5,000, infinity, with a mean of 2801, standard deviation of 920, 0.008419. So look at, that's only a 0.8% chance. So to find rent that high, that's would be very rare. 0.8% is pretty low chance. Okay, so we've spent a lot of time explaining this normal CDF thing. Once you get the hang of it, these really are easy problems, so I hope that your homework goes well tonight. Give it a shot and let me know if you run into trouble.